Welcome to Lyons Township High School Physics AP. Today I've got an example that involves a little bit of your favorite topic, chemistry. And specifically what we're going to do is we're going to figure out if we have a wire, on average, how fast are the electrons traveling to create a current. Okay, so this would be the example I'm going to do with you would be an example of electron flow for a flashlight or your car headlights or something like that. It's going to be a DC current. So we're going to start with some data. I'm going to give you a chunk of wire and give you some information about it, and then we'll talk about how fast the electrons have to go. And then, you know, a good thing to do would be to guess. So they have to go really fast to make a current, they have to go really slow, something in between. Okay, so here's our wire. We'll just draw a cylinder. Okay, so there's our chunk of wire, and we're going to cut a piece out of it. So imagine we've got that little cylinder, and it's got dimensions. It's got an area A, and the height of it, we'll call that x. Okay, so the volume of that cylinder, yep, we're going to need volume, is simply the base area times x. Okay, we're going to say, and we're going to splurge a little bit here. We're going to say it's gold. Okay, so gold. Okay, and I've got some information about gold for you. Let's say the diameter, little d, of the wire is 1 millimeter. So that would be a relatively thin wire, but not too thin. For gold, the gold atom has 1 electron carrier per atom. What that means is if you have the atomic number of gold, the very outer electron is free to jump from atom to atom. That's what's going to carry our current. So it's got 1 electron per atom that is free to move for us. Okay, let's say the current is 10 amps. Remembering that an amp is a coulomb per second. That will actually come into play. We also know the density of gold. Yes, we're going to need density. Density of gold is 19.3 grams per centimeter cubed, and we're going to work in centimeters primarily. The molar mass of gold, yes, your favorite, I'll abbreviate that mm for molar mass, is 197 grams per mole. Yep, we're going to need that too. And finally, we're going to need Avogadro's number. All right, so I'll abbreviate that AN for Avogadro's number, and that is 6.02 times 10 to the 23rd. And the units are atoms per mole. We're going to need that too. Atoms per mole. Okay, so that's all of our data that we're going to be using. Now, and what we're going to do is basically start with this chunk of the wire that we're going to cut out, and we're going to look and see the first calculation we're going to make is how many charges, how many of these free electrons are in that chunk of metal. You got to know that to solve the problem. So we're going to say that's the total charge. So we're going to call that delta Q. How much charge is free to move in that chunk? Okay. How we're going to do that is we're going to take N. Okay. N being the number of electrons per volume. Okay. So that's a volume density of electrons. Okay. Times Q, which is simply the charge of 1 electron, so it's coulombs per electron, which we know that number, it's 1.6 times 10 to the negative 19th coulombs in 1 electron, times the volume, okay, which will be centimeters cubed, okay. So when you do that, the volume here and the volume there cancel. I'll actually make that centimeters cubed. That's the volume. So we'll leave everything in centimeters cubed. Centimeters cubed are going to cancel, electrons are going to cancel, and you end up with coulombs. So in this problem, by the way, a lot of dimensional analysis looking at units, okay? Now, having said that, this equals NQ, the volume, as we said earlier, is the base area times the distance, okay? So now I want to deal with current. Well, how do we get from charge to current? Well, charge is simply, or current is simply the derivative of charge. Now we're going to do it a little more algebraic. We're just going to divide by time. Current is charge over time. So delta Q over time, which is the current, is equal to, we got to divide both sides of this by time. So NQAX over time. Now check it out. What is X over time? That is the velocity we're looking for. That's how fast our little electrons are going. Now, I'll make a quick note on that. This is what we call the drift velocity of the electrons. That's the overall average velocity they have as they drift from left to right or right to left. They actually move way, way, way faster than this. But they bounce around. They bounce from atom to atom, back and forth, as they drift toward the right. We're just finding the net rightward velocity of these electrons. That's our goal today. All right, so having said all that, if we're going to call that V drift, I'll call it V sub D. So we've got current equals NQA V sub D. And what we want to solve for is V sub D. So V sub D equals current, which I know to be 10 amps, over N Q, which I know to be 1.6 times 10 to the negative 19th coulombs per electron, and A, which would be the area of the cylinder, which is going to be pi r squared. So I've got this and this okay. It's N. N is the thing that takes a little while to figure out, okay, and that's where our chemistry comes into play. N again is the number of electrons per volume, or in this case, the number of electrons per centimeter cubed. So we have to do a separate calculation for that. All right, so how do we do that? Okay, well, N, which is, and I'll do the units down here, the number of electrons per centimeter cubed, okay? Well, we're going to first take, and I'm going to write the units out first, and then I'll kind of show you where it comes from. We're going to take the number of electrons per mole, okay, times the number of moles per gram, okay, times the number of grams per centimeter cubed, okay. Now, if you look at that, the first term is the number of charge carriers per atom times Avogadro's number. So it's the number of electrons per atom that are free to move. Okay, those are what we call our charge carriers, times Avogadro's number. Okay, this will be electrons per mole when we're done. Okay, then we are going to have moles per gram. Well, grams per mole is the molar mass, so we're going to do 1 over the molar mass. That'll give us moles per gram. And then grams per centimeter cubed, that's just the density, okay, which you were given in the problem. So for us, N is, well, we've got 1 electron per atom, that's free to move, times 6.02 times 10 to the 23rd atoms per mole. Okay, so that's that first term. The second term is 1 over the molar mass. So it's 1 mole is 197 grams. Okay, and then times the density of gold, which will be 19.3 grams in 1 centimeter cubed. You'll notice a whole bunch of stuff cancels, okay? So like the atoms, the moles, okay, and the grams, and we have what we needed, the number of electrons per centimeter cubed that are carrying our current for us, okay? I'll save you the trouble of doing the calculation. You are certainly welcome to check. But I got 5.90 times 10 to the 22nd electrons per centimeter cubed, okay? That's the hard thing to find in this problem, okay? So once you've got the number of electrons per volume in the gold, now it's pretty easy to find the drift velocity of these little guys. We're just plugging back in to this equation right here, and I will do that. Well, I'll move the board up. Okay. So the drift velocity is the current, which I gave it to be 10. Now, I'll write that out as coulombs per second. Okay, it's in 10 amps, 10 coulombs per second, divided by n, which we just determined to be 5.90 times 10 to the 22nd electrons per centimeter cubed, times Q, which is 1.6 times 10 to the negative 19th coulombs per electron, okay, times the area, which is pi times, now I want to stay in centimeters here. So the diameter is a millimeter, which is 0.1 centimeters. The radius for pi r squared would be half of that. So that's going to be pi times 0.05, okay, squared, and the units will be centimeters squared, okay. Now before we plug all our numbers in, some notes. What cancels out here? Well, coulombs, electrons, and then the centimeters squared and the centimeters cubed partially cancel. You end up with 1 over seconds divided by 1 over centimeters, which is centimeters per second. So our velocity, drift velocity, is going to be in centimeters per second. And again, I'll save you the trouble of plugging these all in. If you plug them all in, you get 0.13 centimeters per second. So the electrons, turns out, they don't go all that fast. Okay, they make a 10 amp current, you only got to move a little over a millimeter per second. And that's if it's DC. If it's alternating current, which means it's going back and forth 60 times per second, they'll barely move a little fraction of that back and forth. So when we talk about AC current, we're talking about electrons literally just jiggling back and forth ever so slightly to make our electric current, which then carries energy from one place to another. So relatively tough problem. Your chem teacher would love it because it's a good review of chemistry. So I hope that was helpful. Thank you very much.